So in the structure we just drew, NO2 minus, we saw that we had two resonance structures. I encourage you to do more. If you did like NO3 minus, right? This is done in the book. There's 3 resonance structures. But one thing those resonance structures you might notice is that they're basically identical. They just have a double bond moved from one bond to another, and those bonds are the same. They're between the same atoms. So that's one type of resonance that's going to be pretty common, is where you're just choosing where do you put, say, a double bond. Do you put it between to this oxygen, this one, or some other bond? But all of those structures sort of are equally good. And they would contribute, might say, equally to the hybrid, if you will. Now, sometimes we get to a point where we have resonance structures, but maybe one of them is better, right? So this is a better structure, right? It makes more chemical sense. It's more stable. Whatever reason we might come up with, right? It's a better structure. Now, one tool that we can use to show if one structure is better than another is what we call formal charges. So a formal charge is, if you will, a fictitious charge assigned to each atom in a Lewis structure that helps distinguish these Lewis structures. Now, we call it a fictitious charge because it's not an actual charge, right? There is no ion here, right? It is just sort of like if we're thinking about, maybe in a polar bond where we have a difference in electron distribution, maybe one side is more negative. It's kind of like that in the sense, but we're just looking at the ideal version of this molecule and where the electrons might be. So the way we calculate a formal charge is that we take the real number of valence electrons, right, that an atom will have. So we do this for each atom in the structure. And we take the valence electrons and we minus the bonding electron, the non-bonding electrons, and half of the bonding. So we only do half of the bonding because we're assuming that they're equally shared, right? And so this is where this idea of we're assuming that all the electrons are equally shared. So in essence, we're assuming no polar bonding. So it's, again, is a guide, right? This helps us, gives us a way to help distinguish this. And we'll see when we use it, right? We follow certain guidelines to help us account for what we would expect chemical reality to be. Now, when you deal with a molecule, if it's a neutral molecule, then all of the formal charges added together should be 0, right? So we should end up with a 0 formal charge. If you have a polyatomic ion like we've done, then the formal charges should add up to that charge. Okay. So let's look at a couple structures here. So here we have HCN, right? Molecule HCN. There's 2 possible Lewis structures that we might draw. We could have the carbon in the middle or the nitrogen in the middle. Now, this is a little bit different. So this is actually looking at explaining why why the skeletal structure is the way it is. So in our first example, we're just going to look at, how can this help us decide, oh, really, is this the right skeletal structure? And then we'll do some examples where we try to decide between resonance structures. Now, so these are not technically resonance structures, so I want to point that out. These are actual different structures because, as you can see, the bonding is different. But it'll get at sort of the point of how we process this. So we're trying to decide between whether carbon being in the middle, like structure A here, or whether nitrogen's in the middle, for like structure B here. So the first thing we do is we calculate the formal charges. So let's do it for A. So for A, we start out with the number of valence electrons. So for hydrogen, normally it's 1. So if we look into the structure, the bonding, so it's making one bond, so it has no lone pairs, so the number of non-bonding electrons are 0. It's making one bond, so that means the number of bonding electrons is 2, but we take half of that. So we end up with 1 here, so we got 1 minus 0 minus 1. We end up with a formal charge of 0. For the carbon, we have 4 no lone pairs, so 0 non-bonding. It's making 4 bonds, right? So it's sharing 8 electrons, 6 from the triple bond, 2 from the single bond. Half of that's going to be 4, so 4 minus 0 minus 4 gives you a formal charge of 0 for the carbon. Now for nitrogen, we have 5 electrons to start with, valence electrons. It has 1 lone pair, so it's 2 non-bonding. It's making a triple bond, so it has 6 shared electrons. Half of that's 3, so 5 minus 2 minus 3, again, is 0. Okay, so we've done the formal charges for structure A. Let's look at structure B. So hydrogen is going to be basically the same. 1 single bond, no lone pairs, so we end up with a formal charge of 0. Now we have nitrogen in the middle. It's again, no lone pairs, but sharing 8 electrons. So we have 5 minus 0 minus half of 8 are 4, so 5 minus 4 is a positive 1. So we got the carbon. So now we have the carbon with a lone pair, it's minus 2, sharing 6 electrons from the triple bond, so that's 3, 4 minus 2 minus 3, we get a negative 1 formal charge. Notice that the sum of these are still 0, right? So the sum adds up to 0, just like it should. The difference is, here they're all 0 formal charges, here we have a 0, positive 1, negative 1. So what's better? Well, our guidelines are, better structures have fewer formal charges, meaning fewer atoms with formal charge. Okay? Better structures have smaller formal charges. So if we do have atoms that have formal charges, we want them to be as small as possible. So the idea is that, let's say, a positive 1 formal charge would be better than a positive 2 formal charge, for example. So if there are going to be formal charges, we want them to be as minimal as possible. And better structures will have any negative formal charges on the more electronegative atom. And this gets into the idea where we have to make chemical sense, right? You're not going to make any sense to draw a Lewis structure where the more electronegative atom is a positive formal charge, meaning it's getting less electrons. That's not what's chemically going to happen, so that doesn't make sense. So if there is negative formal charges, we want to make sure it's on the more electronegative atom. And so, for a lot of reasons, we can see that structure A, right, is the superior structure. First of all, right, we have all 0 formal charges. That's the ideal, right? We have fewer atoms with formal charges. So this one, we have 2 atoms with formal charges. Now, they're just 1, so that's not bad, but they still have more atoms with formal charges, so it seems better. Now, if we look at the negative formal charge particularly, it's on the carbon. If we compare carbon and nitrogen, nitrogen is more electronegative, right? It is, has a farther to the right, has an electronegative higher than carbon. If anything is going to be negatively charged in this structure in terms of the formal charge, it should be nitrogen, not carbon, right? So for a lot of reasons, right, we can say B is not a good structure. And so the skeletal structure of this is going to be carbon in the middle, which is what we would have done anyway, probably, right? This is what should have been our go-to, because carbon is the lower electronegative atom. We follow our procedure. We're going to put the lower electronegative atom in the center. Okay, so that's kind of an overview of formal charges. Now let's put this into action. Okay, so our first problem here is just going to be, we're given some Lewis structures for this molecule. So for N2O, we're given 3 possible Lewis structures, and we're going to try to decide if one is better than the other, and which one is best. So you can see here, when drawing these Lewis structures, we obviously had the choice between, when we had to make 2 multiple bonds, we could have made both of them on the same side, so we could have made triple bonds, or we could have split them up and made 2 double bonds, right? So this is sometimes a choice you might have. Another common molecule that we do this in is CO2, right, which has 2 double bonds. 1 to each oxygen. That's the best one. But we could just as easily put triple bond on one side or the other. So let's try to decide which one has the best using this concept of formal charges. So let's just start over here, and we'll start doing the formal charges. So we're going to have the number of valence electrons. So nitrogen is 5, nitrogen is 5, oxygen is 6 here. So non-bonding electrons. So this nitrogen, we have 1 lone pair, so that's 2. Center nitrogen, none, so it's 0. Oxygen, we have 3 lone pairs, or 6. So we get half of the bonding electrons. So here we have 6 bonding electrons. So we got 1/2 of 6, or 3. Here we have again 6 bonding electrons, so 1/2 of 6, or 3. Here we have only two bonding electrons, just a single bond. So we got 1/2 of 2, or 1. So if we come up with our formal charge, we have 5 minus 2 minus 3, or 0. We have 5 minus 0 minus 3. So that's 5 minus 3. It's a positive 2. Here we have 6 minus 1. So we have, okay, so we have 5, we have 6 minus 1, so 6 minus 7, negative 1. I got a little error here, so let me go back and fix this. This should be 1/2 of 8, right? So we have 0 and 1/2 of 8 because we're sharing 8 electrons around the nitrogen. So we got 5 minus 4. So not a positive 2, but a positive 1. And so of course, you add these all up, they should add up to 0. So let's do the same with our other structures. And I'm just going to kind of go through this. So we have started with 5, 5, and 6. For non-bonding, we have 4, we have 0, and we have 4. For half of the bonding, we have 4 bonding electrons, so half of that's going to be 2. We have 8 bonding electrons, so half of that's going to be 4. We have 4 bonding electrons here at the double bond, half of that's going to be 2. So we have 5 minus 4 minus 2, so 5 minus 6, negative 1. We have 5 minus 4, positive 1, 6 minus 4 minus 2, 0. So again, they all add up to 0. Here we have again 5, 5, and 6 to start with. We have 6 non-bonding, we have 0 non-bonding, we have 2 non-bonding. We have half of 2 bonding, so 1. We have again 8 bonding here, so half of that's 4. We have 6 non-bonding, half of that is 3. So we end up with 5 minus 7. We double check that, so yeah. Negative 2, 5 minus 4, positive 1. And 6 minus 5, positive 1. Again, adds up to 0. So which one of these is the best? Well, kind of a process here, so let's just look at these formal charges. We see that in the first one we have formal charges on 2 atoms. Here we have 2 atoms. Here we have 3. So first thing we're going to do is eliminate this one, right? This is not the best structure. Now what about these two? Are they the same? Is one better than the other? Well, they both have on 2 atoms. They're both 1, so that's okay, right? So they're not the magnitude. So it comes down to where should the negative formal charge be on the more electronegative atom. So we have oxygen and nitrogen. Clearly oxygen is more electronegative. It should have the negative formal charge. So this structure here is going to be the better structure. This one here with the negative is going to be not so good. And so this would be our better resonance structure, where we have the triple bond between the two oxygens and the single bond between the oxygen. So sometimes, it's not always that we have the two double bonds, like symmetry, like we do in CO2, right? Because we're bonding to different atoms, we might come up with a different result. Okay, we're going to close out this section with one final example that's going to lead us into our next section. So we're going to look at the structure of SeO3 2- polyatomic ion. So I've started the process here where we've drawn our skeletal structure with selenium in the middle, bonded to the 3 oxygens. We have a total of 26 valence electrons. So we made our bonds to use up 6. We put 6 lone pair electrons on each of the oxygens using another 18. We had 2 left. We put that on the central atom, the selenium. Right? So perfectly fine. Everything has an octet. All good. Now, I've calculated the formal charges. So for the oxygens, we have 6. We have 6 non-bonding, and we have 1 bond, so half of that is the 2 is 1. So each of the oxygens has a -1 formal charge. The selenium has 6, right? It's in the same group as oxygen. Has just 1 lone pair, so that's 2 non-bonding. It's sharing 6, so half of that's 3, so a +1. Now, notice that they add up to a -2, which is what they should, right? Because this is a -2 ion. So all that's okay. But you notice all 4 atoms have a formal charge. Maybe that's not the best, but how do we know? Well, let's look at the structure. I mean, it seems okay, right? The greater electronegative atoms have negative charges, right? So the negative charges are on the outside. You would expect that. Central atom has the more positive formal charges. That's all good, with selenium being the lower electronegativity. But can we do better? Now, this is going to introduce a concept that maybe we haven't gotten to yet, but this is what we're going to get. So when you start looking at the octet rule, one of the exceptions to that is that certain elements can expand beyond 8. We call them expanded octet complexes. So when we see this, or when we see the possibility of this, is elements in the 3rd period or below. So the 2nd period elements, carbon, nitrogen, oxygens, they are limited to an octet. But as you get down into the next period, so the 3rd period where you'd have things like silicon, phosphorus, sulfur, and even further down where you find selenium in the 4th period, right? These have the ability, if necessary, for a more stable structure to expand beyond the octet because we have the availability of those d orbitals, right? Okay. So let's look at what we might be able to do. So the way that we approach this is we say, okay, we have a positive charge on the center, negative charges on the outside. So one thing we could try is to try to minimize the formal charges, to bring them back down to 0. We can move electrons away from a negative formal charge and toward a positive to try to get to 0. So since selenium has a +1, if we move 1 pair of electrons and create a double bond, right? So we're going to effectively give more electrons to selenium, making its formal charge, it's going to make its formal charge more negative, and we're going to take electrons away from oxygen, which is going to make its formal charge more positive. So what the effect of doing this is it's going to, when the atom you move them away from, its formal charge is going to get 1 step more positive. The atom you move it towards, so the central atom, is going to get 1 step more negative or less positive. So let's see what that does. So now we have the structure, but now we have the double bond here. Now, everything still has an octet, so that's all perfectly fine. But let's look at our formal charges. So we have oxygen, 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 selenium. And so we'll make these, the first two oxygens, the ones that are the same. So these are still going to be 6, 6, 1, and 1. Right, so these are still going to be -1. Now let's look at how the oxygen and selenium that have changed. What do they look like? So they still start off with 6, but now this oxygen has only 4 non-bonding, but it's sharing 4 electrons, so it has half of that would be 2. So 6 minus 4 minus 2. This now has a formal charge of 0. Let's look at the selenium. So it still has the 2 non-bonding, but now it's sharing 4, so it has, it's now sharing 8, so half of that is going to be 4. So 6 minus 2 minus 4, we get a 0. Now, of course, they still add up to -2, as they should because of the charge. But now notice we have only 2 atoms that have a formal charge, and the other 2 are 0. This is better, right? Because less atoms with a formal charge. Now, you might be tempted to start moving more, but the key is we don't want to go below, we don't want to turn the central atom negative, right? We only want to take it to 0. So if this were to have a +2 formal charge, then we could try to do this twice. But once we get it to 0, so once we have the formal charge here 0 and now the formal charge here 0, we're going to stop, right? This is going to be our better structure. Now I will point out there are 2 more resonance structures here that we would technically draw if you were doing this, where we pulled in an electron from this oxygen or an electron from this, so the double bond, in other words, could be here, could be here. Right? We just chose to do it with this oxygen. Nothing magic about that one. So we'd have a total of 4 resonance structures for this molecule, where these 3, the 3 that have the 1 double bond, be better, and the one with the single bonds are not, just not going to be as good. Okay, so we've seen some resonance. What we're going to go into now is we're going to start talking about exceptions to the octet rule. We just mentioned expanded octets, and we're going to get to a few more in our next video.